So thinking back to making pizza, which now that it's noon, we're all being more hungry. Sorry. Here's our recipe. What if we have 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce? How many pizzas can we make? Is that a problem that you can just solve fast in your head? If you sit and think about it for a little while, you can. But that's not something that's just immediately obvious, right? Well, this is kind of the process. What you would have to do is you look at the number of crusts, and you say, okay, 1 crust, 1 pizza. I could make 4 crusts. I could make 4 pizza if I used up all the crust. The dimensional analysis process that you're doing in your head there is you're taking 4 crusts times 1 pizza per crust, and you're ending up with 4 pizzas. 10 cups of cheese we already did, but 10 cups of cheese, 1 pizza for every 2 cups of cheese, 5 pizzas. 15 ounces of tomato sauce, for every 1 pizza we need 5 ounces. So 15 divided by 5, that would give us 3 pizzas. So if we used up all the tomato sauce. So then, knowing that, what's the most pizzas we can make? 3. Okay? When we do this same idea with chemicals, people do crazy things like telling me 12. I can make 12 pizzas because I can add up these 4 and these 5 and these 3, and that makes 12. Does that work? No. With pizza, we see that's dumb, right? Because what happens? You're going along, you're making pizzas. You're making 1 pizza, you make 2 pizzas, you make 3 pizzas, and at that point, you've run out of tomato sauce. So you have to stop. You can't make pizza without tomato sauce. Your boss will fire you, okay? You've got extra cheese, you've got cheese left, you've got crust left. Okay, and this happens in chemical reactions too. We call this, the thing that we run out of, the limiting reactant, because it limits how much product we can make. Okay? Oh, pictures. Do we really need pictures for that? I don't know. We need to put some pepperoni on those pizzas. So tomato sauce is a limiting reactant, or sometimes we call it the limiting reagent. The number of pizzas that we can make, that smallest number, we took each ingredient and figured out how many pizzas we could make. And the smallest number, that's called our theoretical yield. If you had that many ingredients, is it guaranteed that you could make 3 pizzas? No. Because what if when you were getting the sauce and bringing it over here, if you dropped it? What if you sneezed on one of the pizzas, right? Or the light fixture fell onto it, or, crazy things happen, right? Sometimes it doesn't always work out perfectly, and that's why we call it the theoretical yield. In theory, if everything works perfectly, that's how much you could make. So that's the amount of product that could be made in a chemical reaction, and it's based on the amount of limiting reactant that we have. So the limiting reactant determines the theoretical yield. So just like in making pizza, you think about cooking anything. You've got a recipe, you make sure you have all the ingredients. It's pretty unusual for you to have the exact amount for just one recipe, right? If you're going to make pancakes, you've got flour, and you've got eggs, and you've got buttermilk and stuff. And maybe you say, the teenage boy is having a sleepover, and I've got 12 hungry football players here. I'm just going to make pancakes until my eyes start to bleed, right? I'm just making pancakes. You can make multiple recipes of pancakes. Are you going to run out of all the ingredients at the same time? No. That's just not going to happen, right? You're going to have plenty of flour left and you run out of eggs or something. That's just how it works in the kitchen. It works that way in chemical reactions too. Very unusual to have just the right amount of everything. So usually you're going to have one reactant that's going to get used up. When that gets used up, reaction stops. Just like making pizzas, you run out of sauce, it stops. That reactant limits the product. It's called the limiting reactant. The other reactants are called excess reactants because there's extra of them. And we can go back and figure out how much of them gets left over if we want to. So we talked about theoretical yield. The actual amount of product is called the actual yield. We try to be descriptive in our terms here. So what would happen while making those pizzas if you burn one or drop one on the floor and you end up with only 2 pizzas? That's the actual yield of pizzas. Okay? You could have made 3 in theory, but you actually made 2 because you screwed up on one. We use percent yield to help us compare the actual to the theoretical. It's a measure of efficiency. So here's the equation for percent yield, and we'll be using this in lab. Percent yield is the actual yield, how much you actually get, divided by how much you theoretically could get if everything worked perfectly. You multiply by 100. Here we find that our efficiency in making pizzas is 67%. And that percent yield can help us to predict what might happen in the future. If this is pretty consistent, which is really not good, 67%, and you needed to make 100 pizzas for a big party, you had this big order, they need 100 pizzas. If your efficiency is only 67%, you better start out to make more than 100 pizzas, right? Because if you try to make 100 and your efficiency is 67, you're going to end up with 67 pizzas instead of 100. So that percent can be useful in predicting things that might happen. Summary. Yeah, you can read. Yeah, theoretical yield, actual yield, percent yield. Here's the equation in a nicer form. It's the actual yield over theoretical yield times 100. The units on these two don't matter as long as they're the same. Grams on top, grams on bottom, moles on top, moles on bottom. They're going to cancel out. So let's apply these concepts to a chemical reaction. So here's our equation for the combustion of methane. Right? One of these reacts with 2 of these to form 1 of these and 2 of those. Well, what if we have 5 molecules of methane and 8 molecules of oxygen? So here we've got 5 molecules of methane. How many moles of CO2 could we make? Well, we get the ratio here. 1 methane gives 1 molecule of CO2. So if we start with 5 molecules of methane, we'll end up with 5 molecules of CO2. If we had 8 oxygen molecules, well, the equation's on the previous page. It takes 2 oxygen molecules to make 1 CO2. So 8 oxygen molecules. You get 1 CO2 for every 2 oxygen molecules. You could make 4. So the oxygen makes 4, the methane makes 5. Which one's limiting? The oxygen, the one that makes the smaller. So this strategy here, there are different ways of solving these limiting reactant problems. This is the one that the book gives. So when we have quantities of reactants as masses, we're going to have to use the grams to moles thing. So grams of A to moles of P product. Grams of the other reactant to moles of that reactant to moles of product. You can compare at this point moles of one product, moles of product from the other reactant, and whichever one is smaller comes from the limiting reactant. And then you would take whichever is smaller and continue on and find the mass. Personally, what I prefer to do, because it's only a tiny bit more work, but I think just conceptually it's simpler, I prefer to go on to mass of P here and mass of P there. And then look at these two. Which is smaller? There's your answer. Okay, so that's the method I'm going to show you. I'll put boxes here. And you may have learned a different method of looking at ratios of things, but I find that students tend to get confused by that, and so what I like about this is we're going to keep with that pattern, grams to moles to moles to grams. It's just we're going to do it twice, once for each reactant, and then we're going to look at the amount of product. Whichever is less, that's the amount we can make. If this one is less, then we look back and that came from reactant A, then reactant A is the limiting reactant. So let's do an example of this. Fuel mixture used in the early days of rocketry consisted of two liquids, hydrazine and dinitrogen tetroxide, which ignite on contact to form nitrogen gas and water vapor. How many grams of nitrogen gas form when 1 times 10 to the 2 grams of hydrazine and 2.00 times 10 to the 2 grams of dinitrogen tetroxide are mixed? Things got complicated fast, didn't they? This is a stoichiometry problem, right? There's a reaction occurring, and we've got masses, we've got quantities of reactants and products going on here. We're going to need a balanced chemical equation. You might as well just do it right away. So the reactant formulas are given to us here. N2H4 and N2O4. I'm going to write mine up here. N2H4 and N2O4. And it's forming nitrogen gas and water vapor. What's the formula for nitrogen? N2. N2. And water vapor, H2O. Is that balanced? No. It's got to be balanced. So we look here, 2 nitrogens plus 2 nitrogens is 4, and over here I've only got 2. But then we were also told if there's an element by itself, leave it for last. So maybe we should leave that guy for last. Let's look at oxygen. How many oxygens? 4. And over here there's only 1. So we need to make there be 4. Now let's take care of the hydrogens. Here's 2 times 4. There's 8 hydrogens over here, and there's 4 over here. So I need to put a 2 in front of that. And that's not changing the oxygens. They're still okay. So I've got hydrogen and oxygen balance. Now I'll take care of the nitrogens. So 2 times 2 is 4, and 2 more is 6. So I need a 3 over here. So there's our balanced chemical equation. So here we've got a mass of N2H4, and we have a mass of N2O4. When they give you masses of 2 or more reactants, it is necessarily a limiting reactant problem. So what we're going to do is we're going to calculate the amount of product that can be made with this reactant and do a separate parallel calculation, find out how much product we can make from this one, and then we'll just look at the answers and see which is smaller, and that will be the answer for the amount of nitrogen gas that can be made. So we're going to start out, I'll write out one of these paths. We're going to start N2H4, grams to moles to moles to grams. So grams of that to moles of that to moles of what we're looking for, which is what? How many grams of nitrogen gas? It's always good to calculate the right product. Moles of nitrogen, 2 grams of nitrogen. The path for the other one's going to be real similar. It's just going to have N2O4 here and here instead. Okay, 1.00 times 10 to the 2 grams N2H4 times 1, 2, 3. Grams to moles to moles to grams. Grams, oops, not moles there. N2H4. You really, really need to write all these units out. That's not an H, that's an N. And grams. We fill in the denominator by looking at the units in the previous numerator. And when we're careful with our units, we do not get things upside down, which is the common mistake, that people multiply instead of divide or vice versa. Where do the numbers for this middle term come from? The balanced chemical equation. So what should I write in front of moles of N2? 3, because that's what it says up here. What should I write in front of N2H4? 2. The first and last conversion factor are molar masses. Well, nitrogen, that's 2 times 14.01, so that's 28.02. And then the hydrazine is 2 times 14.01 plus 4 times the hydrogen. It's tempting to round hydrogen to 1, but don't do it. 2 times 14.01 plus 4 times 1.008. 35.052. That's the mass of 1 mole of hydrazine. So that goes in here. 35.052. Then we can calculate 182 divided by 35.052 times 3 divided by 2 times 28.02. Sig figs, the mass of nitrogen will be our final answer. So it's okay to round. Here, this number has 3 significant figures. This had 4, I'm sorry, 5, this had 4. These are exact, so I'm going to round my answer. It says 119.9. That's going to round to 120. Let me show you. 119.908. I need to round to 3. That's going to be 120. That's an ambiguous 0, isn't it? You can put a decimal point there and make it not ambiguous. A lot of people understand that notation. What's the best thing to do with that number? Scientific notation. So 1.20 times 10 to the 2 grams. That's how much nitrogen if we use up all the hydrazine. And we do a parallel calculation with the dinitrogen tetroxide. So 2.00 times 10 to the 2 grams of N2O4. And we'll have moles of N2O4, and we'll have moles of N2, and we'll have grams of N2. And I'm slanting down. I'm sure that means something. And maybe it's that I'm feeling pessimistic. N2O4. I'm writing on half of an iPad mini. It's just, it's very small. Moles of N2. Now, what's convenient is this last term, exactly the same. So we can just copy that down. The molar mass of nitrogen has not changed since we started doing this problem. Again, middle term, balanced chemical equation. So this is, 3, and the bottom is 1. Now we need N2O4. So 2 times N plus 4 times oxygen two times nitrogen, 4 times oxygen, 92.02. So that goes over here, 92.02. These units are going to cancel out. 2 EE2 divided by 92.02 times 3 times 28.01. This will also have 3 sig figs in the answer. 182.699 is going to round to 183 grams of nitrogen. Now we come to the super, super challenging part. Which number is smaller, 183 or 120? 120. So this is the answer. That is the theoretical yield. Which of those reactants is the limiting reactant? It's the N2H4. So you do these two calculations, you find the one that gives the smaller number, you go back to the beginning, and that's your limiting reactant. So that's our limiting reactant. Sometimes the question will ask you for that. On a lab, pre-lab question or something, if it asks you what the limiting reactant is, you have to specify it somewhere. You can't just circle this and say, oh, there, I'm done. If it says, what's the limiting reactant, I'm okay with you circling that and putting LR. Somehow, though, indicate to me that you are conscious of what's going on here and that you know which one's the limiting reactant. Any questions?